Welcome to the presentation of the paper Modeling Ambiguous Assignments for Multi-Person Tracking in Crowds. I am Stadler from Karlsruhe Institute of Technology, and this is joint work with Jürgen Beyerer from Fraunhofer IOSB. I start with a short motivation before the main contribution of our work is presented, that is, a new association method which models ambiguous assignments and treats them separately from clear track detection matches. Then, two additional tracking modules are introduced which further improve the performance: a camera motion-aware interpolation technique and an adaptation to the motion model. After that, I show experimental results and finally will conclude with a summary. Most of the multi-person tracking methods in literature follow the tracking by detection paradigm. For all track detection pairs, a distance measure is calculated and saved in a distance matrix. Then, usually the Hungarian method is applied to solve the assignment problem. In this procedure, all assignments are made at once, which leads to tracking errors in ambiguous situations that arise when multiple possible assignments have similar distances. Such situations emerge especially in crowded scenes where the targets share similar spatial positions and appearances. In contrast, we propose a new association approach that treats those ambiguous situations separately. Additionally, two tracking modules are introduced to further boost the overall performance. The proposed algorithm to find ambiguous situations builds purely upon the distance matrix of tracks and detections. Thus, it can be incorporated in any tracking by detection-based method. First, we look for similar assignments, track detection pairs with similar distance in terms of a delta threshold, 0.1 in this example. Tracks 1 and 4 and detection 4 build similar assignments, as well as track 6 and detections 3 and 7, and also tracks 3, 7 and detections 2, 6. After finding all similar assignments, we keep only the ambiguous ones. We term assignments ambiguous if the numbers of tracks and detections differ. The highlighted example is not ambiguous since both of the two tracks and detections can be matched. Then, we differentiate between ambiguous detections, where the number of detections is less than the number of tracks, and ambiguous tracks, where more detections than tracks are involved. For example, the detection 4 is termed ambiguous as it is not clear if it should be assigned to track 1 or track 4. To resolve the ambiguous situations, we investigate different approaches for ambiguous detections and tracks. The first strategy for resolving ambiguous detections is to simply delete those detections, arguing that they often occur under occlusion and might be inaccurate. Another possibility is to follow a multi-hypothesis approach that builds and maintains hypotheses until the situation is clear again and no ambiguous assignments are present anymore. In the multi method, the assignment of an ambiguous detection to multiple tracks is allowed. For assignments with ambiguous tracks, also three techniques are examined. In the delete strategy, again, the involved detections are removed. Also, a multi-hypothesis approach is followed. And as third method, an initialization strategy is investigated, in that unmatched detections start tentative tracks, which have to be confirmed in consecutive frames before activation. After all ambiguous situations are resolved, the remaining clear matches are assigned with the Hungarian method. Now I talk about the additional tracking modules we have introduced. We found that two components are important for a high tracking performance: a camera motion compensation if videos with severe camera motion are processed, and a mechanism for track interpolation after occlusion. However, most trackers in literature which apply an interpolation do not consider camera motion. Instead, the last detected box before occlusion is copied into the frame where the track is reactivated. Then, a linear interpolation is performed. Finally, the interpolated boxes are simply copied into the respective frames and camera motion is neglected. This can lead to inaccurate boxes as illustrated in the figure. In contrast, we propose a camera motion-aware interpolation that uses the transformation matrices of the CMC model to improve the accuracy of the interpolated track boxes. Instead of copying the track boxes, those are transformed with the matrices of the CMC model into a common middle frame. Then the interpolation is done, and after that, the interpolated boxes are transformed back to the respective frames, again with the use of the transformations of the CMC model, which is depicted as W prime in the figure. Another component of our tracking framework is an adaptation to the motion model. In literature, a Kalman filter with a track state modeling x and y positions, aspect ratio, and height of the bounding boxes is often used. Of course, inaccurate detections introduce errors in the state estimation. We find that the last detection before severe occlusion is often inaccurate, especially in crowded scenes. This can lead to a growing or shrinking bounding box in the following track prediction and make a reactivation after occlusion impossible as shown in the figure. As we observe that a wrong estimation of the bounding box height poses the most problems, we follow a height preservation technique that simply fixes the box height in track propagation. With this strategy, identity preservation can be improved as shown in the toy example, where the track is successfully reactivated after occlusion. Now I talk about the experimental results. First, let's have a look at the different strategies to resolve ambiguous situations. As a baseline association technique, the Hungarian method is applied on all possible assignments. One can see that only the delete strategy improves all tracking metrics for handling ambiguous detections. Similarly, the initialization strategy for ambiguous tracks boosts all metrics. When combining the two methods, the performance can be further improved. In comparison to the baseline, significant gains are obtained with a plus of 2 points in MODA and IDF1 and a plus of 1.6 points in HODA. Here, a qualitative example for an improved tracking performance with the delete strategy for ambiguous detections is shown. The standard association assigns an ambiguous detection to the wrong track, as can be seen in the middle frame of the top row, which leads to an identity switch. Note that inactive tracks are marked with dashed lines. In contrast, our approach deletes the ambiguous detection, depicted as dotted purple box in the middle frame of the bottom row. Both inactive tracks are propagated with the motion model until the situation is clear again, that is, when again two detections are present. With this strategy, the identity switch can be prevented. In this table, the impact of the additional tracking modules can be seen. It is observed that interpolation is important for achieving a high tracking performance, as MODA is increased by 1 point even with the standard linear interpolation. The proposed camera motion-aware interpolation further improves the performance since the interpolated boxes are more accurate. Note that in sequences with severe camera motion, MODA is improved by more than 2 points. Our height preservation module further improves the tracking performance. Furthermore, the proposed tracking framework shows a good generalization ability among various detectors and on two datasets. Both on Mod 20 and Mod 17, significant improvements with one-stage RetinaNet, two-stage faster RCNN, and the crowd-specific model CrowdNet are obtained. Our tracker, MAA-Track, for modeling ambiguous assignments, also shows very competitive results with respect to other methods from literature. State-of-the-art results are achieved on Mod 17 and also on the very crowded Mod 20 benchmark. This shows that the separate treatment of ambiguous assignments is a promising research direction for future works. To summarize, we introduced a novel association method that models ambiguous assignments, which is purely based on the distance matrix. For resolving those ambiguities, different strategies are investigated. Furthermore, a new camera motion-aware interpolation technique and an adaptation to the motion model are introduced to further improve the overall performance. It is shown that the proposed tracking framework has a good generalization ability among various detectors and datasets, and state-of-the-art results are achieved on two mod benchmarks. Thank you for your attention.